Welcome back. So last time we were discussing this particular sample problem. We were discussing how to find the moment of inertia of geometries, and we had just done the rectangular geometry last time, and we had found the expression for that. And we now wanted to. This is the problem where we left off, was finding the moment of inertia for a circular cross section. Having said that, I want to, so remember that the moment of inertia is different than the polar moment of inertia, but sometimes the expressions can be very similar. So I just want to go back. I'm just trying to look for it. Yeah. Right. So here we had introduced the polar moment of inertia, and then we had found the expression for circular cross section, which came out to be pi r square, r to the power 4 by 2, r being the outer radius. Okay, so there are obviously, so now Iz, which we know already to be integral of y square dA over the area. And the question is how to evaluate this. Obviously, you can go back to doing something that you did similar to the last example, and you can repeat it. But here we can take advantage of a very equation that is valid in the case of circles, and that is now. So remember, so we had just, I showed you j in this case would have been r rho square dA, right, integrated over the same area, where rho square is for any given location y square plus z square. It is this quantity. So the centroid obviously being the center of the circle. So I can rewrite j as integral over a y square plus z square dA, and this obviously breaks up into two areas. Sorry, this is a summation of two areas. Sorry, a summation of two integrals. And the thing is, these two integrals, they look different because you have a y square and a z square. But in the case of a circular cross section, these two integrals, when you finally evaluate them, they will be actually identical, right? So this is obviously, the first one is Iz, and the second one is also Iz. So j is actually equal to 2Iz. So from here, we don't have to calculate, we have already calculated. C was the outer radius. Maybe I'll just, to keep it consistent with that example that I showed you, I'll make it capital R. So this is now pi r to the power 4 by a 4, right? Okay. So those were two examples, and we were looking at the problem of pure bending. And it is, despite the mathematical simplicity it bestows, it is not the most common form of bending that you find. Okay. Not the most common form of bending, and that is because in most bending situations you will have an associated shear stress present, and most of the time the shear stress will also be changing with location. And so usually shear stresses are present. Associated now with bending, one of the classical associated experiments, so associated classical experiment in this context, and I'll use this to drive home a point about how shear stresses are involved. So associated classical experiment in mechanics is the 3-point bending test. And okay, let me, so what I did is I went online and I found one nice video which will show you how this works. So this video is on YouTube. I'll just pause it for a moment. This is the device. This is okay, you cannot, oh sorry, I cannot use my laser pointer, but you can see the yellow color beam, and there are two rectangles which are the supports, and then you have a force carrying member that is impinging upon it. So you can see the beam bending, and this is the associated software which is looking at the stress and the position plot. And yeah, this keeps on going till it fails. Okay, so the only thing I wanted to do here is to show you that this is a classical experiment which is used to calculate the flexural rigidity of beams. And I was saying that in the case of pure bending, so pure bending is not a very usual phenomena, and I wanted to tell you the reason for it. And the reason is actually straightforward, that even in the simplest of cases, for example, the 3-point bending, where I can make a schematic for the system where this is so this is the schematic for the video. L by 2, this is a force P, and then you have obviously reaction forces at the two supports, right, that is balancing it at every moment. So the process is quasi-static, so at every moment there is equilibrium there, so that the process is not very fast. And in this case, if you wanted to draw a diagram, so just a second, I'll do some, I don't have too much space, so I'm just going to utilize it smartly. I'll tell you why I use the different color. Okay, so for example, if you wanted to plot the shear stress, just a second, I'll just quickly finish this drawing. What the? Okay, so now if I were to plot the shear stress V, what you'd find is that the shear stress remains negative, and then suddenly it jumps right at the middle to a certain value, and finally goes to 0 at the end, right? And it maintains a constant value like this. And what does the bending moment look like? the bending moment, and the bending moment I'm drawing using the red color, and I'm going to draw it on the same plot because I just want to save space here. The bending moment is going to look something like this, which is, and these are two, this is a straight line, this is a straight line, so it looks like a triangle. So, and finally the beam is going to bend out. It's in a different view. So this beam is going to bend somewhat like this, right? That's a pretty bad drawing. Okay, that was not very good either. Okay, now, yeah. So this is sort of the bent shape. I just carried it on both sides for clarity. That's all. So this shows you that even in such a simple case where you just have one force acting and two very simple supports, even here your bending moment is changing. So your assumption of pure bending is not applicable here. So what do? Is our entire derivation now useless? Do we have to now go through the whole process all over again for a situation where there is shear stress also present and a bending moment present? Do we have to redo the entire thing? Well, you probably can guess that the answer to that is a no, and there must be a reason why we were studying this pure bending case, and that is because for the engineering theory of elasticity, we are going to beam bending, we are going to make the important assumption that the beam bending stress distribution, okay. So for general cases, we will proceed with the assumption, this is W is width, okay, with assumption that the beam bending the bending stress distribution remains valid even when the moment varies along the beam, that is, a shear stress is present. So what bending stress distribution are we talking about? So for a general case, we will proceed with the assumption that the bending stress distribution, which bending stress? The one that we encountered in the flux shear formula, this bending stress distribution. Here MB was constant, remember. So this bending stress distribution remains valid locally even when this moment is changing along the beam, right? So in a more generic case, shear stresses will also be present. So if you were to draw, for example, if somebody wanted to ask you to draw a more general case, drawing which showcase the fact that Okay, so if this was the more generic situation, then if I were to just draw the moment here on the positive face, I'll draw a positive moment. So I will orient it along the z direction, and if I had to figure out what is the right arrow direction, then I have to apply my right hand rule, and you will see that the direction of the moment will be this. So this is my MB. These are two alternate drawings. So you either choose this one or you use this one, whichever one you become more familiar with. And on the other face, you have, this is going to go, the direction of the moment vector will be opposite, or if you want to look at it from the perspective of the curved arrow, then you will draw it like that. Okay. So you have a moment acting on the other face. You have, if I had to create a positive shear on this face, then it would be oriented along this. So this is my V, and here it would just go downwards. This is V. In a more generic situation, this V is changing across the length. So this is function of x, and by the way, this is just a dx element. And here your moment is also going to be changing across the two faces. So if V is present, your moment is changing across the length, and it will be some value here, and it will be a slightly different value here, right? You will have to apply the Taylor series expansion to find out what is the value here. But in the case of a pure bending situation, the shear stresses are for a given constant moment. If V were to sort of disappear, then if you wanted to draw this drawing, so you'll find this drawing in a lot of books. Okay, this is giving me a lot of grief. Wait a second. I'm just going to draw it now. And if the positive moment were acting on it, then how does the stress distribution look like? Well, the stress is 0 at the center. This is a square. I deliberately drew a circular cross section, and on this face, on the upper side, the stresses are inwards because it is in compression, and this is because my sigma xx just varies as y. So my sigma xx is linearly related to y, right? And on the other side, this side is acting under tension, so the arrows face outwards, right? And similarly here on the other side, I'm not drawing it, but you can draw it for your completeness if you want to. So I hope this clarifies a very important problem, which is how do you calculate these important values when it comes to real problems. So maybe we should just take a look at one sample problem. Okay, so let's do that. Okay. Sample problem states that there is a beam which is supported at the two ends, and there is a uniform force or a uniform weight acting on it. So, if I had to draw that, it would look something like this. Okay, so we have a W naught acting here. This W naught is say 5 kilonewtons per meter, and let's say the length of this is 4 meters, and you have, so it's very easy to work out what are the reaction forces. In a problem, I mean in a classroom setting or exam, will not give you out, but you can just simply calculate it here. This is rather straightforward. The reaction forces will be 10 kilonewtons each. Okay, it's a very simple symmetric situation. The question is, what is the maximum shear stress? The maximum bending stress due to bending that this structure is going to feel. And okay, one more thing I have to give you. What is the cross section like, right? So if you have to find out I have to give you the cross section. Okay, so let's say the cross section is rectangular, and this height is 120. This height is 120 millimeters, and this distance is 80 mm. Okay. So what is the maximum bending stress that this body is experiencing? I want you to give it a moment to think. This problem should remind you of, I believe, I can't remember exactly, but I think I have done this problem in class. And even if I am not, that this is, if you go to, at this point, I'd say good place to revise material from chapter 3. Okay. And this is actually a problem, worked out problem in the book. It's given as problem 3.5 in my book. Okay, so you want to check what problem it is. Okay. So, of course, in the book it doesn't give this part, right? So it's in chapter 3. It is only concerned with finding the bending moment diagrams and the shear stress diagrams, right? So I just draw the stresses here. I'll make two diagrams, one for V and one for M. And you should be able to work this out. If this is my L, then this looks something like this. Okay. So it starts off from some negative value, ends up at a positive value, and is joined by a straight line. For this, the shear force diagram. The bending moment diagram here looks, okay, this, the bending moment diagram looks something like this, and this high point here, this is of course a circular or parabolic in nature. It is parabolic in nature, yeah. And this high point is given to you as max was M max was W naught L square by 8. Okay, so first thing we have to do is we have to calculate I, Z, rectangular constant cross section, and you can just apply the formula that we have found a few pages earlier. We discussed it in the last class. So it's BH cubed by 12. Please calculate it. It will come out to be 11 point. Okay, so those of you who are watching the video at the moment, I would suggest that you work out the problem. You pause the video, work out the problem, and match with my answer. Okay, it's a really straightforward problem at the moment, because this value is already known to you. You should have paused. You could have paused it any other moment, but at least you should do it now. So this, according to my working out, thing, it's IZ was 10 to 11.52 into 10 to the minus 6 meters square, and sigma max is basically my bending moment, the max bending moment into the Y max, right, which in this case is H by 2. Divided by IZ, and you just put a plus and minus over here. Why do I put a plus and minus? It's because of this particular situation, right? Here, see, your top face will feel a compressive and a bottom will face a tensile, but those both are maximum. So for a given problem, you can just write it as plus and minus. The top part, one face will, one part of the beam, one half of the beam will face a compressive and the other half will feel a tensile stress. So that is why I have this plus and minus. So if you work this out, you should get something like plus and minus 52 MPa. In an exam problem, we'd probably ask you to find stress at a different point. So we'll just point a different location here and ask you to find a stress value over there. Okay, where are we now in time? Okay, so the next topic, and I'll just introduce you to that topic and we'll complete it in another lecture, is the topic of composite beams. So till now, we had been assuming that whatever the cross section is, right? So if you had an arbitrary cross section, A, it had to be symmetric and all that, but it also had to be uniform. Okay, so till now, beams are uniform. Uniform meaning there is one E associated or one modulus associated with this entire problem. But you can have a more complex scenario where half of the beam is made of one material and another part is made of another material. How will you work this problem? Okay, so I'll end here. We will carry this on in tomorrow's class. Okay, thank you, and be safe.